So what I would like to do is to talk a little bit about some of the work we have been doing in sulfur as a battery material. I'm sure most of you probably know quite a bit about the topic already, but you don't have to know anything about it to to listen to the talk. So uh, since there have been multiple energy storage talks, sulfur appears to be a wonderful material. The chemical reaction is extremely simple. You just take 2 moles of lithium and then react with 1 mole of sulfur, and then you get the lithium sulfide. And you go back and forth, and these produce uh, a tremendously high energy density theoretically. In reality, it's very hard to do. So in fact, very few lithium sulfur batteries can even reach 260 if you want any meaningful cycle life. So the reaction is incredibly difficult. And but we that has because of these numbers, people have never really given up on the material. Recently, there's an extra reason to work on sulfur. Is it because of the supply chain concerns? The metal oxides are primarily produced overseas, particularly in Asia, China, Japan, Korea, and Taiwan. Sulfur is everywhere. So on paper, this would be one way for us to get out of these supply chain concerns. Um, it's more than free. People will pay you to take it away. So, but people have known this forever, and why haven't we enjoyed the lithium sulfur batteries or sodium sulfur batteries for that matter? Um, One simple fact people don't realize is just how insulating sulfur really is. So sulfur, everybody knows sulfur is insulating. It's a molecular crystal. Uh, it's really a great dielectric material. Uh, to calibrate your expectation, sulfur's conductivity is about 10 to the minus 18. That is a very, very small number. So if you say I teach in the nano engineering department, so imagine if you make a thin layer of sulfur of a nanometer thick, if you work out the math, the resistance will still be like a 10 to the 10. So as wonderful as nanomaterial is, contrary to common belief, making sulfur in the nanoparticle is not as helpful as you would hope. So we can't really move electron across a layer of sulfur. That's virtually impossible to do, no matter how small you make it. So if that's the case, how do we turn sulfur into a battery material? Since a battery is an electrochemical device, we have to move electrons and ions around to get electricity out. But how do you get electricity out of almost a perfect insulator? By the way, in case you didn't know, sulfur is the most insulating element in the entire periodic table. So that's not very helpful at all. So what do we do to kind of get around this problem? There are a couple ways to do that. So we will talk about the two general approaches people take, including us, to make sulfur more active. So the first is to take a liquid electrolyte, and this is the discharge profile of sulfur with lithium sulfur with a liquid electrolyte. And it has a working potential of about a 2 volt, 2.2 volt. And it has tremendous capacity. And this, first of all, this is a small miracle. Actually, you can get capacity out of a perfect insulator. But that's on the flip side, the battery's cycle life is terrible. So this is a very old plot from precisely 10 years ago, made by a company called Cyan Power. You probably could guess why they gave their company's name Cyan Power. Is a sulfur ion power. That's where the name came from. And if you read this plot, this is a log scale. Okay, the actual energy density. Remember, lithium sulfur can get to 2600. So if we get to 500, which right now is still the goal, the energy density and the log of cycle life falls over on a straight line. So in other words, if you get a 500 watt per kilogram lithium sulfur battery, it works for precisely 4 cycles before it's dead. So this is not very helpful because the world does not need a 4 cycle lithium sulfur battery, no matter how much energy it holds. So why is it so? The reason is the sulfur, which is the S8 ring, when you react with lithium sulfur, you make a series of what we call polysulfides. And many of you probably heard of this. And what you only heard about it is everything bad about it. Say, we make a sulfur, we have, lithium metal, and it just circulates between the anode and the cathode, it was short, do also terrible things. But I want to remind you that it's not all terrible. The fact that this is a perfect insulator, this dissolution mechanism actually activates it. That's the only reason that you can actually, the battery works for 4 cycles at all. Otherwise, you wouldn't get anything out of it, out of a perfect insulator. So this dissolution mechanism makes sulfur work, also kills it. So it's kind of, it's a two sides of the same coin. So this is not very helpful because, we discovered a mechanism to make sulfur more active. The mechanism also inherently decides that the battery is not going to last. That doesn't sound too exciting. So about 10 years ago, the Department of Energy formed this something called the Battery 500 Consortium. As the name might imply, that we try to make a 500 watt-hour per kilogram battery. And the sulfur is one of the candidates. And so back then, that was before actually when Professor Goodenough was still around. And in fact, he worked with many of the researchers in the consortium. And that was before he and Professor Whittingham were awarded the Nobel Prize for their work on lithium batteries. So what do we do in the consortium is that traditionally most of the lithium sulfur battery work has focused on making a nanostructured sulfur in carbon as a cathode material. Again, like I said, making it nano itself does not make it active. The fact that you put the sulfur into like a nanoporous carbon will give the sulfur more surface area to work with, where it can react with to pick up an electron and combine with lithium. Unfortunately, as that inverse log plot, the inverse log plot is just another way of saying it's an exponential decay. So, so we try very hard, try to improve, say, this plot. Is it possible we can move away from this line and to a happier place? Okay, that's one approach. The other approach is we don't work with elemental sulfur. So in my own group, we actually work on something called S-pen. So I will show you, this is a form of sulfur where the sulfur is given electronic and chemical activity, and so that it's a better behaved. So the S-pen is an interesting material. It's very easily made. So you heat up a polymer called a polyacrylonitrile with elemental sulfur in a tube furnace under inert atmosphere at about 350 to 400 degrees C. You get this black powder. So if in case you're not familiar with the polyacrylonitrile, that's the precursor people use to make carbon fibers. So at the Georgia Tech, uh, Professor Satish Kumar is a world-renowned expert in PEM material. So if you make this material, you get this discharge curve, and the capacity does not look too exciting. It's a 550 instead of over 1,000. But what's amazing is that the material, unlike elemental sulfur, the material cycles forever. So as a quick recap, I just want to remind you, the S-pen material works like this. And it does not dissolve anything into the electrolyte. It's a true solid material. Elemental sulfur dissolves, and that's why it gives these plateau shapes. But in sulfurized PEN, it's a single plateau. And it's a solid-solid reaction. So when you have a solid-solid reaction, it's wonderful because now you can make a battery without too much electrolyte. So what the people have found with elemental sulfur, because the polysulfide needs to dissolve in order to move the reaction forward, as you can imagine, the battery behavior is heavily dependent on how much electrolyte you add in. But if you add a lot of electrolytes don't really store any energy, and that would kill the cell level energy density. So I just want to remind you, keep in mind there are two different kinds of lithium sulfur batteries, and we primarily work on this type. So the key to this is to find a new electrolyte that will allow this material to be stable. I can tell you if you find the right electrolyte, and the electrolyte we work on is this what we call localized high concentration electrolyte. So it's a lithium FSI dissolved in diethyl ether mixed with BTFE, which is a non-solvent. So this type of electrolyte innovation has been the essence of the work we do, not necessarily on the S-pen material itself, but rather it's to allow the S-pen material to work as intended. So you will see that this S-pen material cycles for 1,200 cycles in this electrolyte without decay, without any decay. You remember that was the inverse relationship between cycle life and energy density? Well, this material does not degrade. And this electrolyte also allows lithium metal to cycle very reversibly. So this is the Coulombic efficiency of lithium metal. So now we have an electrolyte that allows the cathode to cycle reversibly and allow anode to cycle reversibly. So sounds like we solved all the problems. Actually, we haven't, but that's the but it's a progress. So this particular electrolyte is great in the sense that in order to make a lithium sulfur battery work, we not only need to keep the sulfur happy, we also need to keep lithium happy. So this electrolyte does both. So this electrolyte produces very smooth lithium, very dense lithium. And then what is the secret sauce that keeps the sulfur, the S-pen material stable? These are the X-ray photon spectroscopy, and we check the surface species on the electrode. You will find out that in this high concentration electrolyte, on the cathode surface, we make lots of lithium fluoride. And then we also observe a variety of sulfur species on the surface. Without going into too much detail about exactly the reaction mechanism, I want to tell you what this particular electrolyte does is to form a protective layer on the cathode surface. that isolates the sulfurized PEN material from the electrolyte. It doesn't really work in a diluted ether electrolyte. This is actually, uh, if you look at this, this is diluted ether electrolyte. In this particular case, you make a less lithium fluoride, and then the surface species are actually different because here we make a lot of sulfate and here we make very little. And it's this type of species that form a coating on the cathode surface that allow it to be reversible. So that's kind of what we did for a few years. We tried to, discover new electrolyte, understand the chemistry interface, and then we actually made a real battery. It's a 2 amp hour cell, and this cell actually has a real energy density somewhere between 260 to 300 watt per kilogram, and it's not 500. But the cycling stability actually is very good. So this work was done probably 4 or 5 years ago, and this performance remains one of the best in the literature even to this day. So we still continue to work on it. Now, you may ask, it's only 300, it's not 500. So what can we do to turn it into 500? So I used to work in industry, and for everything, every technology we develop, there has to be a roadmap. So what's plotted here is energy density as a function of cathode loading. So we need to make a very thick cathode. And these numbers are the amount of electrolyte we add. We need to add a very tiny amount of electrolyte in order to produce a high energy density cell. The bottom line is, however, our S-pen material, as stable as it is, the capacity is a little too low. So if you redo the modeling, but assuming the electrode capacity to have higher capacity, the number is higher, then obviously the energy density of the cell will increase. So instead of, over here, you have to have a tiny amount of electrolyte to get to the green zone. Over here, the same electrolyte will get to 350 or even 400. The question then becomes, how do we increase the sulfur in the material? It turned out, in order to answer that question, we need to figure out what exactly is S-pen. That turned out to be a really difficult question to answer. Because unlike a metal oxide, the material is made by heating a polymer precursor with elemental sulfur. So we make these complex polymer-like material. It has some electronic conductivity because there's conjugated double bond structure. It's not crystalline, so we can't use traditional techniques like X-ray diffraction to understand its structure. It's also heterogeneous. It has a lot of different sulfur functional groups. The actual structure is more complicated than this. We're still working very hard understanding the molecular structure of these polymers and a way to react with lithium. Where does the lithium go? And what functional groups does the lithium react with? And in fact, during the first cycle, we even observed some irreversible transformation, including the formation of H2S during discharge, which is not great, after which the material becomes more conducting. Now, how do we put in more sulfur? It turned out the secret of this structure is it can bind with very short chain sulfur, like 2, 3, not quite 4 sulfur chains. And based on this mechanism, recently we have made a composite material we call the CS-SPEN. So this material has some characteristics of carbon-sulfur composite and has some characteristics of sulfurized PEN. And with this material, And we can increase this capacity, from S-pen to CS-pen about 20%. It doesn't sound like a lot. It's actually a lot. If we could increase the cathode material by about 20%, we are safely in a region to produce a lithium-sulfur cell with the energy density somewhere between 350 to 400 watt-hour per kilogram, which will be wonderful. However, there's a limit to how much extra sulfur we can shuffle into the material. As you shuffle more sulfur into the material becomes less conducting. And in fact, if you look at this discharge curve, if you put a lot of sulfur into it, you start to see this shoulder here, which is the characteristics of elemental sulfur. Something we don't like, because we worked on S-pen material to stay away from elemental sulfur. Turn out that if we shuffle a lot of sulfur into the material, there's no magical pill. The materials start to behave like a mixture with the elemental sulfur, which will reintroduce a lot of the degradation mechanisms suffered by elemental sulfur. So what do we do? The other approach we take is to move to solid state sulfur. We use a solid electrolyte instead of liquid electrolyte. Solid state very safe. There's no shuttle effect because there's nothing to dissolve. There's no polysulfide dissolution. And you can make a very high energy density material. It turned out that this is even more difficult to do than liquid electrolyte. Because in a solid state, we can't use the dissolution mechanism to get around this poor conductivity anymore because nothing moves. To make it even worse, sulfur expands a lot when it makes lithium sulfide. In the liquid electrolyte, that's not a big deal because the polysulfide dissolves and reprecipitates. In a solid state, if something expands and shrinks, then the structure cannot recover. So you create a lot of issues at the interface. So what my postdoc at Jinping discovered a couple of years ago is that we have to do something about the sulfur itself. What he discovered was something really interesting. He reacted the sulfur with iodine. He made a red liquid that looked like this at 65 degrees C. Sulfur has a melting point well over 100. Now we have a solid-state battery material with a melting point of 65. And even more interestingly, this red color actually indicates to us the material may be electronically conducting. So if it's electronically conducting, that solves the conductivity problem. If it melts at 65, maybe if our battery degrades, we can reheat it to 65, remelt the material. That will make the interface great. Again, basically, we can heal any interfacial problem due to volume change. And that's precisely what we discovered. So we did a lot of thermal analysis. We determined, the melting point is 65. And then we use this type of series ratios to determine what is the ideal ratio for the material. And then we freeze the material, try to decide what did we actually make. People always thought sulfur and iodine do not react. They form a eutectic. If you recall what's the definition of a eutectic, is you mix two solids together, the melting point is suppressed. However, when you freeze the liquid, the two materials will go back to what they were. That's not what happened here. Instead, we discovered in X-ray diffraction a peak at a very low angle. What does this mean? This means sulfur and iodine form a mesostructure with a repeating distance on the scale nanometers. So what is this material? And the structural model is if you take certain sulfur elements out and create a defect, you can put an I2 monomer into there. In case you didn't realize, iodine has precisely 4 times of the atomic mass as sulfur. Sulfur is 32, iodine is 128. So exactly 4 times. So if you put in one I2, you can take one S8 out. We think that's the material we have made. So we did a lot of characterization work on the material. We use electron paramagnetic resonance spectroscopy to catch the free radicals. Turned out when we make the material is very rich in free radicals, unlike elemental sulfur. And what does that mean? We measure electronic conductivity, the material behaves like a semiconductor rather than a perfect insulator. So this is wonderful, even though 10 to the minus 7 does not sound very exciting. If you repeat the calculation I did at the beginning, now if you make a 1 nanometer thick film, you will see you are in business. Now the electron actually can go through 1 nanometer film without any difficulty. So finally, we have a solid state material that's electronically conducting enough. It's rich in free radical, and it can be remelted. So the material has the potential to address some of the most difficult problems suffered by elemental sulfur. And here's the proof. So when we make a solid state material, usually we mix a lot of powders together, the active material, the carbon, the solid electrolyte. Now we have one material that we can melt. So that's why we make a electrode that's far more uniform than just sulfur itself. This is intuitive because one of them can melt, they can flow everywhere. And then the electrochemical performance is amazingly good. We can discharge these material. We almost get a theoretical capacity, and then we can discharge this material at an extraordinary rate. Even at the several C, meaning we can discharge these solid state batteries within a few minutes to the order of an hour. The low rate performance is usually a major issue with solid state batteries. But now we have what we think is an inherently more conducting material. Now, the final proof is that can our proposed mechanism, that if the batteries start degrading because there's still volume change, can we reheat and reset the structure? And the answer is we can. So over here, you see every 50 cycle, when the batteries start degrade, we warm it up and then we remelt it, and then the impedance will drop. And we have more direct evidence here. So you will see when we first make the material battery, the electrode is 19 micron thick. And after many cycles, the electrode has increased in thickness to 22. And you will also see there is a gap between the cathode and the electrolyte. That's not good. That gives you, in a local hotspot, the increases impedance. However, if we reheat it, you will see the thickness partially recovers and the interface is healed. This is because we can remelt the material, because the sulfur iodide material has a melting point at 65 degrees C. With this, we can reset the impedance, which is showing on the left, and then we can reset the microstructure. So we continue to work on solid-state lithium-sulfur. There's still a lot of work that remains to be done. So with that, I just want to wrap up. elemental sulfur itself can never make a battery. In order to make a battery, people have tried lots of different things. If you make a nanostructured sulfur carbon composite, you put in a liquid electrolyte, it does cycle, it does discharge and charge, not for long. And it relies on a dissolution mechanism. Basically, you picture sulfur as like rock, but the electrolyte is kind of like a corrosive agent. You gradually dissolve it away and then reprecipitate it. In that case, you don't need to rely on the electronic conductivity of sulfur to have a chemical reaction or electrochemical reaction. This problem can be solved in two different ways. You can put the sulfur onto a polymeric structure that will give it a conductivity. With the right electrolyte, the material actually cycles very well. There's a limit to how much sulfur you can put on there, and which limits the energy density of the battery. Alternatively, you can also study sulfur as a subject of material science. In that case, we use doping. We make new sulfur-containing materials. This is not really doping. Sulfur iodine, the superlattice, is a brand new material. And this material has better electronic conductivity, and its melting point is also low, so that it can partially heal itself. So finally, I just want to thank all the people who collaborated with us. Studying sulfur is very difficult. As I said earlier, unlike a traditional metal oxide, you cannot use X-ray diffraction very broadly to study the structure. We have to turn to new tools. We continue to develop new tools with our collaborators. For example, if you ever worked on electron microscopy, it's very difficult to put a sulfur-containing material into a vacuum because it vaporizes. Before you see it, it's gone, and it contaminates your system. So it's actually a really, really difficult thing to do. And the work has been funded by Department of Energy, as well as our industrial partners, their membership in the SPEC Center. The liquid electrolyte work has been funded by the Battery 500 Consortium.